All right, well, let's dive in. So I don't know if we actually did we say anyone would be leading today's? Oh man, whoops. Does anyone?
Easy.
Do you want me to lead? Oh,
No.
boy. What?
No, it was too hard.
Yeah, it's exactly.
I mean, I think we should just talk about the definition of a Bayesian game and a Nash Equilibrium for a Bayesian game. Mm-hmm.
You mean, are you talking about 3.1?
No, I think we're moving back to the previous week if we're going to talk Bayesian game.
That's what I thought, yeah.
Yeah.
We're
Well,
going to do that.
But as I wrote in the channel, I have been catching up on the reading because I didn't have time before. And it seems like most people don't understand some of the notation that they used in the definition of a Bayesian game. So yeah. I think that's why we're thinking about moving back to that.
Yeah, we should definitely revisit it. I remember that it made sense to me once. So let's see if we can re-achieve that.
Yeah.
Yeah.
So does someone who has at one point understood it pretty fully want to share their screen?
Sure.
Yes. I just...
So you all see definition 25.1?
Yep.
Yes.
Bayesian game. Set of players, set of states, and for each player, a set of actions available to player I, that is the set AI, a finite set of signals that may be observed by player I. So the signal function from the set of states gives you a signal. This is what we talked about with a state, for example, being that it is raining, and the signal being you noticing that your head is wet. And from that you can deduce several things, but you can't be for sure that it is raining because it could be somebody peeing on your head or something like that. So
I have a question there, sorry. Other word for signal, what was the other word for signal?
Type.
Which is annoying.
Yeah, type, yeah.
So, I mean, later on the next page, you can all see my screen. There's a player that we refer to as I, Ti, type Ti of player I. So, which means that they're basically using signal as synonymous as type. Which is quite annoying, or super annoying, but let's not get annoyed. And then we assign probability measures to all of the states. Right. So if we see a certain signal, we assign probability to a state of nature. So if we see that our head is wet, then we assign a probability larger than 0 that it is raining. And then a preference relation on the set of probability measures. Okay, so where you try to maximize your expected value, really. Okay, so the thing we want to do here is, in order to define a Nash equilibrium of a Bayesian game, we want to define it in terms of a Nash equilibrium of a strategic game, because we know what that is. And so then we need to reduce the Bayesian game to a strategic game. And the way we do that is to, instead of considering players, probability measures, and our signals and the signal function and so on, we expand the set of players So we create a strategic game, a G star, that has a player that has I, Ti as players. So we not only have our players I, but also the possible signals that they can receive. And where the set of actions of each such player is AI. And so this is where the action profiles come in as the Cartesian product over all of the players, and then all of the possible types or signals that that player can receive. This is a bit confusing, but anyway, I think it becomes clear once we start looking at the exact definition. So a Nash equilibrium of a Bayesian game is a Nash equilibrium of the strategic game, defined as follows. We have the set of players, as I said, and the set of actions of each player is AI. And let's think about what AI is. Well, there we just said what the set of actions is. Oh,
it's the same AI as for
the same definition of the Bayesian game, right?
Yeah, exactly.
Yeah, it's okay. So they still have the same actions available to them. I mean, it doesn't matter which signal you received, you're still going to have the same set of actions available to you. But you're going to order them differently, because the way in which you will order them depends on the signal that you have received. So the preference ordering of each player ITI is defined by you prefer A star over B star if and only if the lottery of A star and TI is larger than the lottery over B star and TI. And so lotteries work like this. They assign a probability of the probability pi of omega, so the probability that the state of nature is omega, on the condition. So this is conditional probability. This is not a division or anything. This is the probability of omega happening given that you have observed Ti, and so that you are in the state of nature, the inverse of the signal function, or the inverse image.
So wait, are you sure that it is a division? Because like when you have conditional probability, it was a while ago since I did statistics, but can't you arrange stuff so that you essentially get this formula that is division? Or like maybe they explain somewhere that it is conditional probability, but I always interpreted it as division.
I mean, they say here the thing in words, and I remember that's why I deduced that it had to be conditional probability. So I mean, the answer to your question is no, that I'm not sure, but I'm convinced. Yeah, so here, if we read it in the text, it says the posterior belief of player I together with an action profile A prime or A star in G star generates a lottery over blah blah. The probability assigned by the lottery to this action and the state of nature is player I's posterior belief that the state is W when he receives the signal ti.
Yeah, and wait a minute, let me just pick up a thing and I can argue then.
Yeah.
And so pi is the signal function, right? And then
Tau is the signal function. Pi is the probability function.
Probability of that being the state.
Yeah.
And that's within the context. Is that a global thing, or is that like, person, the ith person's belief of the state?
So it's dependent on the player. So each player assigns a different probability to them being to the likelihood of different states of nature.
Yeah. And so that would come after the signal function has been after the signal has been interpreted.
After, yeah, I mean, the probability function is given beforehand. Pi is given beforehand. But the thing is that beforehand they haven't received any signals. And so they update their probabilities when they receive signals. And that's why I'm quite convinced that this is the conditional probability, because it assigns the probability of this when omega is actually one of the possible states of nature that could provide you with this signal. And it's 0 if omega is not at all one of those states of nature that could provide the signal that you're seeing.
So can I just share my screen for a short while? How?
There's a share screen green button in the middle of the bottom of
there. Right, the simplest one. So I'm thinking about this. Can you see my Firefox?
Yep.
Nice. So like this, maybe you're all familiar with this and I'm way behind, but if we have like the prior belief of something of a theta happening, and we observe right, so when we learn new information, we are able to formulate the conditional probability of what we're actually interested in, which is this. Can you see my mouse? Nice. Mm-hmm. In terms of the probability of the reverse and the two separate events happening. And I might be wrong, but I think that this is what they are exploiting, and this is why it turns into a division instead of conditional probability. But I might be completely off here.
Yeah, that's a really good point.
So this is how you update beliefs in in face of new evidence, essentially.
Right. So, are you saying that PI that the numerator is like what is the px given?
So the px would be the probability of having a wet head, while theta would be or x would be the event that your head is wet, while theta would be the event that it is raining.
And so, like in our formulation in the textbook, it says, pi omega, that is omega, I believe, right? No, not omega. Is that it?
Yeah.
W, okay, yeah. So pi omega would be equal to px given theta p theta. Is that correct?
Yeah, exactly.
And so if that's true, then that's probably what they're exploiting.
Yeah, but the thing is that here they have like two terms in the numerator, and I only see one in our definition, so I'm not completely sure. It doesn't match up completely, but they are talking about posterior beliefs and updating your beliefs in favor of new evidence, and like this is the thing that I'm aware of that deals with that. So this is why I'm trying to bring it up. But I don't understand either, so I'm not sure.
I mean, what would make sense is that the probability that it should assign is the probability of omega given that you see the signal, right? But the problem is that it's not clear exactly what x, for example, would correspond to. I think you would, that can't be the probability of your head being wet. It would need to be a different state of nature. And you would need to look at this graph of dependencies of probabilities of the different states of nature, and based on the signal you have received, you update your probability distribution given that evidence.
Right.
So, it could very well be that it is simply divided by, that might make a lot of sense, actually.
We can go back to the PDF.
Yeah.
Cool. Well, I can say I don't fully understand it, but I think I have a general idea. I don't
I kind of agree when it comes to this part, because they are basically updating their beliefs in face of new evidence. Exactly how it's done, not sure if we actually need to follow the details there, but I still don't understand this. What is it even supposed to mean?
Yeah.
You mean this?
Just this.
Okay. I don't know what you're talking about when you say this, but
oh, maybe you don't see my annotations.
Oh, I see.
Now they're moving around, so I have no idea what's happening.
I'm sharing my screen, and then I'm sort of shifting windows on the Mac, and that kind of
right.
It's a bit strange, and maybe I don't see your annotations.
Can you see mine?
No, I don't see anybody's annotations.
Do you see mine? No,
I think they're on the previous screen. If you move it to the previous screen.
Yeah, there you are.
That's me.
Yeah, if you want to get some annotations going on Wittgenstein's criticism of Russell's theory of judgment, then there you go. But with respect to the game theory, so we assign this probability to the action that player I does when they have seen the signal coming from omega, and that the state of nature is omega. So that's I mean, that's a specific action, right? That's an element of AI.
What is A star? Maybe we should start there. I thought it was a vector, but I might be wrong there.
So A star is
2 rows down from what you highlighted.
exactly. So that posterior belief together with an action profile A star.
So then A star should be a vector, right?
That was
An action profile is a vector of all the different actions.
Yeah, I mean, so A star is the action of player J and the signal generated by the state of nature omega in the profile A star, where A star is the set of actions available to, I mean, it's an element of AI, I'm pretty sure. So the way we should interpret this, anyway, I mean, the notation is kind of confusing because they're using A as if it were a function.
Exactly. So I guess they are taking this particular player's action from the action profile A star.
Yes, exactly. Yeah.
Right. Yeah. Then it makes more sense.
So A star,
of course.
A and tau J omega is a particular action. And in particular, it is the action of player J tau omega in the profile. So where profile...
They wrote the answer to my question.
Yeah.
Okay, yeah, thanks.
But profile is a bit ambiguous to call it a profile. It's a set of action profiles. I mean, isn't it just their set of actions? Well, okay, they have a profile of actions, which is dependent on which state of nature they're in. Yeah, they don't mention like profile. They don't say explicitly. Do they say explicitly what they mean by profile?
I think they do in the when they define pure games, but I might be wrong.
Oh no, they do it here. The two primitives of a Bayesian game are a set of players and a profile of sets of actions. So this is a set of sets, and
no, it's a vector sets. Or because they put it in parentheses.
No, I don't think that's what they mean when they put parentheses like this.
Math.
Yeah, I mean, generally you never say that things are vectors. You just say that things are sets, and then sometimes those sets are vectors. But in general, it doesn't really matter.
Sure.
And in particular, in this context, it doesn't matter whether it's a vector or a set. But the point is that AI will generate a set for every signal that you receive. And those sets will be the sets of actions that you can do if you receive a signal, TI.
Yeah.
And therefore, you will assign a certain probability to this action if you are in that state of nature. So, I mean, this is an element of this set. So omega is a particular state of nature where capital omega are the sets of states of nature, and A is the sets of profiles for each player, and the sets of profiles, or a profile is in turn a set, and when we give a particular player and a particular signal, we get an action.
Yeah. Yep.
Wow.
Yeah.
Wow. That was amazing.
Yeah. So.
Oh, God.
So we're on chapter 3, right?
Yes. I'm also Martin, you said you may have to drop off at some point, you said?
Mm-hmm.
8 p.m.
And that was sort of at this point. But I mean, yeah, I can stay a bit longer.
Okay.
But thanks for reminding me.
For sure. I'm yeah. At least the general idea of this is I like this. I like mixed strategy, Nash equilibrium, the concept.
Yeah, they're pretty cool. So we looked at mixed strategies. So wait, let's see exactly.
Mixed strategy versus pure strategy, I think, is the first.
Our basic model of strategic interaction in this chapter is a triple that differs from a strategic game as we previously defined it, in that, the utility function is given by their preferences over a set of lotteries. And so now somebody's pinging me on Slack. And that is the meeting that I'm supposed to. Okay, so I'm gonna jump onto.
I'll share my screen, guys. But thank you, Martin. That was very, very helpful.
Thank you, guys.
Thanks.
Okay, time for me to share my screen. I can find the right buttons. Okay. All right. Make it a little bigger. So, okay. So where are we? Here we go. So, mixed strategy, Nash equilibrium. I am not going to do as good of a job as mine. That's okay. So, I guess I can start by saying, so the difference between like a mixed strategy and a pure strategy, as I understand it, is previously we were working with pure strategies where you basically have one action that you choose with like
100% probability.
100%, yeah, with 100% probability, right? That's And then mixed strategy, you can have many different ratios of probability for your different actions that you choose to follow. So someone want to help out with the math notation would be awesome.
It was so inaccessible.
Yeah. I have to say I got a lot from the Coursera, like at least the general concepts from the Coursera thing.
Yeah, I watched the Yale one. It was really nice.
Yeah, because this is just very, very, very dense.
And honestly, the notation they use, like it would be much easier to follow if it was a bit more standard. I think it's like it's not only being like lots of math; it's also honestly not very well written.
I thought the same thing.
Cool. So, I mean, we can skip over notation and kind of talk about the general concepts.
Yeah.
Does anyone have like some other notation resource?
Good idea.
Like, I didn't check the Coursera, so I don't know if they use like good math notation or what.
I have no idea. Sorry.
Yeah, maybe that's something I think. What I'll next time I do my research, I'll try to find just like Wikipedia notation and see if Wikipedia notation is better for just each one of the definitions. There's something in there. Really easy to Google. So yeah. So we have the mixed strategy and we have the pure strategy, right? So we're now focusing on mixed strategy. So if we go down and we skip a bunch, okay, the mixed extension of the strategic game. Was this clear to anybody?
Yes, like more or less. So you're essentially, let me annotate. So like you're essentially saying that instead of just having the, like, I'm pretty sure that these parentheses actually mean vector now that they are here. So you have, like, in the strategic game, you have a vector of sets of actions. So each player will have a set of actions, and then we arrange it into a vector where each element is the action that each player can take. So we just extend that to say that, yeah, the vector of actions that they can take is like it won't be just a simple set. It will also be as they write here, the set of probability distributions over AI.
Yeah.
So that's the different strategies that they can pick, and instead of so then when we have updated, like, how a strategy can look, then we also have to update the preference or the utility function, so that it's essentially, and like, it takes a probability distribution and assigns a real number. So it's essentially the expected value.
Mm. Okay.
And the rest, I didn't get this part.
Yeah, no, that does make sense though, and that is helpful, because we do clearly have to, we're adding in the probability, so we have to take that into consideration when we think about the utility for each action.
Exactly.
And it's generally So, and this is the utility, right, for each player I, and this is the set of all the utility functions.
The parentheses here indicate that we have a vector. So for each player I, we will have a different utility function.
Yeah.
And the utility function takes tuples of probability distributions. All right. So it will take a tuple, like, for player I. So for player 1, it will take a probability distribution, which is essentially its strategy. I don't know what I'm writing in, to be honest. So this is the probability distribution that player 1 has chosen as its strategy, and it continues with all the other strategies, but all these are going to be probability distributions over actions instead of pure actions. And so it takes lots of those and maps it into real number. So given lots of, like, all the players' different probability distributions, you will get an expected value for a particular player. And then we have n different of those functions, so we can get it for each player.
Yeah. Okay, cool. So I'll move on to the next part. So definition, mixed strategy, Nash equilibrium. So the general concept, I think they actually go, should I skip a little bit of words to go into where they talk about the Bach versus Stravinsky question?
Sure.
Just so that we can, because I think they use a lot of math and explain things really deeply, but then we can just kind of talk about, I don't know if they do a good job of explaining it here. So this is essentially taking a game that we're familiar with, the Bach versus Stravinsky, or Battle of the Sexes, and including some kind of including a mixed strategy outcome. And with that, what you can see is, this goes through the whole kind of reasoning, and they of course come out with different, they include the percentages. That was not a very insightful explanation, but let's see.
They skipped over.
What does degenerate mean, by the way?
Yeah, I don't know.
Let's see, because they must mention it up here. Let me know if you find it.
You could use this.
Yeah, it's true, but it goes crazy when I do that.
Right.
Like it just starts like it does a very, very fuzzy search, so it maps to tons of pages. Okay, I can. Fine, I'll search for the. Did I just skip over it? Oh my gosh, I'm sorry. So where did you see the degenerate? Non-degenerate. Let's hope. Okay. Here, this is the first reference to.
Very nice explanation. Of course you know what this means.
Yeah, exactly.
Okay, I'll try my Google skills. Be right back, or whatever you say.
Yeah. Okay. I'm not even gonna really hardcore
They're
attempt.
openly hostile to us as the reader at this point.
I know.
They're just like, you don't need to know what it means.
Oh my god. Yeah, that's so crazy. So why don't we? Would we be able to, just looking at this Bach Stravinsky, while we're figuring out what degenerate, non-degenerate means, find the mixed strategy equilibrium, which I believe is, is it subjective? Actually, this is more of a question.
Is it subjective?
It's clearly not. So yeah, that would be very bad. So how would we find the mixed strategy Nash equilibrium? Do we know?
So I know from not from this book, but from elsewhere, that in order for something to be the mixed strategy Nash equilibrium, it needs to have identical payoffs, or every component of the mixed strategy needs to be a best response for the player choosing it. Isn't that right?
Yep.
For each player. And then the only way for multiple strategies to all be a best response is if they have identical expected payoffs. So both of those things I know are true. And I'm guessing that goes into, so right up here, the book says that, I don't know what gamma 2 here means. I think it's expected payoff. So it says that the expected payoff of Bach times 2 equals the expected payoff of Stravinsky. I think that is saying the same thing as what I'm saying. Oh no, stop. Yeah, right there. You see it? It's like
yeah.
So I think that's saying the same thing as what I said, because the expected value of Bach is, I guess, 2 times the probability that you choose Bach, and then the expected value of Stravinsky is 1 times the probability that you choose Stravinsky, and so then setting them equal is suggesting that the expected values are equal, which is basically, like I said, saying the same thing. 1 second. Okay, this one.
And this is the probability of choosing.
Yeah, I just don't understand. Sorry, I didn't mean to interrupt you. Go ahead.
I was just going to say, So this is the probability of choosing Bach, and this is the probability of choosing Stravinsky, and this.
No, that's player one's mix, and that's player two's mix.
Okay.
Yeah, exactly.
And then this is Bach. This is Stravinsky.
Yeah, exactly.
This is Stravinsky.
I just don't understand where the threes come from, because everything here is using like double payoff, right? So like as far as like the really basic algebra goes, I don't see how 2 times basically P equals Q, which is just using different notation.
Yeah, I think that it actually requires you to assume, you have to kind of, to do the basic algebra, you have to kind of know what the other's probability is going to be first. So like a way that we could test it is we could say assume this person chooses Stravinsky, player two chooses Stravinsky 2/3 of the time, and player two chooses Bach 1/3 of the time.
Guess and check? Is that what we have to do?
I mean, that's like the stupid way to do it, where you assume like you know. I mean, that's how, and then you can check player one. Okay, does that actually hold, and what would the probabilities be there? And then you check again. You say, okay, player two, assuming that does player two change, their decision? And then you say no, and then you're happy. And so I think that's the way that they show how to do it in like when they're first introducing it with Coursera.
Yeah, the yellow one seemed to do something somewhat similar. It's just really weird from the book, because it was like, so the sentence says, we must have 2 gamma 2b equals gamma 2s, and thus gamma 2b equals 1/3. It's like, how is that and thus anything? you skipped so many steps. There's such a yada yada yada.
So gamma 2, okay, what is gamma 2? Suppose that gamma 1.
Gamma 2, I believe, is the probability that either you or your partner chooses.
Here, this is it. Suppose that gamma 1 and gamma 2 is a mixed strategy.
Right.
Equilibrium. So that's I think the important part, where like they're doing that kind of guess and check thing, where they're just assuming this is the Nash equilibrium, and then kind of checking it, and they say, yeah, but I mean, I still don't fully understand that clearly.
I mean, there's a bunch of last week I erroneously thought that we were doing mixed strategy, so I watched a bunch of videos on it, and there's like some ways to do the math, but I just don't remember them right now.
Yeah, exactly. So I'm curious. So maybe for next week, definitely we'll like dive a little bit deeper into mixed strategy, Nash equilibrium. And
I found a video of a dude who goes really deeply into it.
Cool. Yeah, please post that.
But he actually does it a little bit differently, because I think that he was talking so if it's a Bayesian game, how does using a mixed strategy affect the equilibrium? So that's that's
adding yet another level. Does chapter 3, by the way, do we know, does chapter 3 cover Bayesian game mixed strategies?
I don't know what correlational, there's like the next one is like correlational equilibrium or something, and the next one's evolutionary equilibrium. I don't know.
Cool. Well, I would say we're getting relatively close to the time. Did you have any luck, by the way, Jack, figuring out
if I had what?
Did you have any luck figuring out that
right. Yeah, I wrote in chat that then my internet connection was unstable, so I dropped off. Maybe you still see it?
Let us begin. Oh, here we are. Found on Wikipedia. Of course, one can regard a pure strategy as a degenerate case of a mixed strategy in which the particular pure strategy is selected with probability 1 and every other strategy with probability 0. Okay, I see. It's a degenerate case of the mixed strategy. Okay.
Yeah.
So it's just talking about later.
The only one that is a pure
So is degenerate case just writing a pure strategy in mixed strategy notation?
Yeah, exactly.
Yeah, and you can see that it actually, in the book, it covers this. Apologies for going super fast, but it kind of covers something related to this. It's not exactly that. Clearly, that's a degenerate case, but this is mixed strategies as pure strategies in a perturbed game, which is essentially like if you have enough pure strategies, you can cover the strategy format. Anyway, but I think let's quickly go over what we should do for next week. And I would say like re-tackle mixed strategies, I'm happy to kind of go over some kind of examples might be the easiest way to start getting a sense for it, because the definitions are telling us a little bit here. I'll stop my share actually.
If anybody finds a good mathematical notation of a mixed strategy game, or at least one that's better than the books, we should go over that, I think.
Yeah, definitely.
And then the other thing was, because Bach or Stravinsky is so simple, if there's anything else we can like glean from it as far as like not guessing and checking and like deriving the correct strategies, because like you know how I like skipped a step. I would like to. If not, then I don't really care. And then otherwise, maybe do other examples out of the book. I don't know what else to do other than those two things. That's not enough.
Yeah, I think that sounds reasonable.
Okay, which exercises out of the book look the most promising? We should stick to 3.1 as far as exercises go. You guys agree?
Yeah.
So the exercises that we've got to choose from, aside from Bach or Stravinsky, we've got guess the average, an investment race, guessing right, airstrike. I don't know. I guess maybe just like you could just look at them and then whichever one you understand best, you can volunteer to explain. Sort of like we did last time, but it's okay if two people converge on the same one in this case.
Yeah. Good idea.
I think that sounds fine.
Cool. Okay.
Nice.
So see you next week.
Yeah, definitely.
Sounds good.
Cool. I'll copy your notes card.
Yes, I just did.
Good. Perfect.
Cool. All right. Well, thank you, everybody. Take it easy.
Bye, Tom.